Hi all, I'm Daniel Nemeth, and I'd like to talk about cosmic fibers and the parametrization of time in CDT. So, causal dynamical triangulations, or CDT, is a theory of quantum gravity, where we glue together four-dimensional simplices to build up a space-time. And the theory is, and the dynamics in the theory is led by the Einstein-Hilbert action. And after discretization and the weak rotation, we get this Reggie action. The Reggie action is described by three coupling parameters. And during the simulations, typically we fix the volume, and as K4, which is playing the role of the cosmological constant, it has to be tuned to its critical value. When we tune K4 to the critical value, we can find the theory in the function of the other two couplings, and this is what we call a phase diagram. Now, we have four distinct phases. Phase C is the so-called de Sitter phase, where we could recover the mini-superspace solution. Phase A is the so-called branch polymer phase, where the volume of the distinct foliations are decoupled from each other and the correlation length goes to zero. Phase B is a collapsed phase when all the volume is gathered on one single time slice of our model. And CB is the bifurcation phase, which shows a very interesting structure. There are condensations of vertices, and if we have a large enough volume and a large enough number of time slices, then the volume is also gathered and this forms a blob structure. What do we know about the geometry? Well, during the discretization and the Reggie calculus, we got rid of the metric tensor, so we don't have coordinate system. We have an extremely fractal structure, and we can measure only distances of simplices. We have a periodicity, especially in the time direction due to the foliation, but also in the space-like directions, we can define periodicity if we consider toroidal spatial topology. So for a torus, we can imagine this as a cube. On this picture, you can see the three-dimensional section of a four-dimensional torus. We can introduce boundaries in x, y, yz, and xz directions. And the torus can be imagined as an infinite periodic structure. These boundaries can be defined in every direction. And with the help of this, we can analyze spatial distributions of simplices and values related to simplices. However, these boundaries are not physical, and they are also not unique. But this will come handy when we introduce the scalar field. So let's see how we introduce the scalar field in our model. We have the Einstein-Hilbert action, with SR being the Reggie action, the geometric action, and we have the scalar field related term, which looks like this. And after discretization, we get this form where phi plays the role of the field, and this B is a so-called boundary matrix. When we did not consider any boundary matrix, then we run measurements for a dynamical field, then we did not observe any significant effect. Even if we introduce the field into many directions, so for example to x, y, p directions, still there was no effect. But with the help of this boundary matrix, which works as follows, imagine that simplex I and simplex j are neighbors. Every simplex has 5 neighbors. So if there is a link between simplex I and simplex j, and if this link goes through a boundary, then simplex I sees the value of simplex j as +1 compared to its value. If it goes to the other direction, then it sees as -1. And if simplex I and simplex j is connected by a dual link which does not crosses the boundary, then they see the value of each other as they are. If we introduce such a matrix into the action, then we saw that the dynamical field introduced some interesting behavior. When this value was not +1 but a larger value, then already for one field we observed some significant effect, and the system went through a phase transition. Right now I would like to talk about the not dynamical but the fixed geometric system. So we have a fixed binary geometry, so the Reggie action will be just a number, and we consider only the classical solution of this. If we expand the action, then we can see that there are three terms. The first term is related to the Laplace operator, which is formed as the degree matrix, which is just the degree of the simplices, which is 5 times the identity matrix, minus the adjacency matrix. That adjacency matrix encodes the connectivity. If simplex I is next to simplex j, then the value of this matrix is +1 and 0 otherwise. V is the volume of the boundary, which is quadratic in Vij, and we have also a term which connects the field to this boundary via this boundary or jump vector. The minimum of the action can be found when the field value takes this form, which means that the field has to satisfy the inhomogeneous Poisson equation. As we know the Laplace operator and we know the jump vector, we can solve this equation. And after solving this equation, we will get a field distribution for every direction. So let's see what we get if we introduce the field into every direction, x, y, z, and t. And let's compactify y and z direction so that we will have just a two-dimensional plot of the field distribution in x and t directions. We will get such a structure. Well, the structure shows some voids and some fiber structures. So this is why we call it cosmic fibers, because it resembles the cosmic structure that we see. Every point on this plot is a simplex. And the time slices are represented by colors, as we have 20 time slices. This picture represents the structure and the field distribution inside the de Sitter phase. Now, we have to redefine the field in a way that, let's call it alpha parametrization. It's a transformation of the field, which makes the field to go from 0 to 1 in every direction. So here the horizontal axis is the time direction, where the alpha parameter goes from 0 to 1, and the vertical axis is the x direction, where also the alpha parameter goes from 0 to 1. It's interesting to note that here, the alpha parameter, the field distribution in alpha parametrization towards the time direction aligns with the original slicing, but it doesn't mean that it is equal with that. Let's look at the distribution of it in other phases also. If we decrease the gravitational coupling constant, we enter the bifurcation phase. In the bifurcation phase, we have this large blob that we discussed before and condensations of vertices. And we see that the value of the field, again in x and t directions, seem to be condensated at a certain value of this alpha parameter, which is a quite interesting thing that we don't have any structure here. In the B phase, where all the volume is located at one slice, we see a similar behavior, that there is a condensation because there is only one slice which contains all the volume, and it seems that the field value is also, the field distribution is also localized. In A phase, that can be seen in this plot, we can see that there are some inhomogeneously spread little condensations. I don't know if you can see it because it's very dark, but there are some inhomogeneity in this plot, but there is no causal structure, there is no fiber structure that we saw earlier. Let's get back to the phase C for a moment. So we mentioned this alpha parametrization, where every single point is one simplex, and we have this vertical line. If a simplex touches this vertical line, then it means that it is at a constant alpha value, and this forms a hypersurface. And this defines a fully connected hypersurface for a constant alpha value. And if we shift this hypersurface, it means that we actually take another alpha value, and we can look at the evolution of this hypersurface. And if we consider the field distribution in x, y, and z directions, and we consider this evolution of this hypersurface in x, y, z directions, then with the colors that I was showing before, we can look at the evolution of this distribution. And we will get, are we supposed to get, yes, we will get such an animation. Every single color represents a fixed alpha value hypersurface in x, y, z directions. And it's also, you can see that these values go around voids and they form some connected causal structure. this seems like the visual representation of the path integral itself. It's quite interesting. We can also measure the number of simplices in these connected hypersurfaces. Let's call it alpha profile. It's similar to the volume profile. In x, y, z, and 3 directions in the C phase, we can see that we have a more or less flat profile with some fluctuations. This is for one certain configuration, so it's not an average of an ensemble of configurations that we typically do. And you can see that there are some long-range correlations, and but typically, if we would average over many configurations, then we would see a flat profile probably. In phase A, we can see that there are some alpha values where it is large, and then there are some other values next to it which is small. It shows that there is no correlation between adjacent alpha slices. In phase B, we can see this compactification that not only the volume, but also the value of the scalar field is located at a certain value. In every single direction that we measured, it was compactified such that you can see it's very, very located at a certain value. What is more interesting than that is the bifurcation phase. If we are far from the de Sitter phase, so it's 1.5, the K0 is 1.5, we can see that we have a very narrow peak. As we increase the gravitational coupling constant, so we go towards the de Sitter phase, we can see that the width of these peaks is increasing. Now, if we go even closer, we can see that the width of the peak is increasing more. So the conclusion from this is that further we are from the de Sitter phase, we are more and more compact and more condensed in the field distribution. Imagine this hypersurface in alpha. It is fully connected, as I mentioned, and we can look at imagine this evolution as some shift of these simplices. If there is a simplex which has 5 neighbors, and out of these 5 neighbors, n neighbor is on the boundary, if we move the simplex to the other side of the boundary, then out of these n neighbors, 5 minus n will go to the boundary, and these n will leave the boundary. So it means that we shift the boundary by some unit. Now, what is interesting that this can be also imagined as a 3-dimensional Euclidean elementary move. So that I described to you right now is actually analogous with a 3-dimensional Euclidean move in this hypersurface. So it means that we can define a 3-dimensional, or we can define a hypersurface in every single direction, which is true for every direction. But if we consider the time direction, then it means that we can define a hypersurface in the time direction, which is not equal with the original foliation. It separates 2 regions of the configuration. One is past, and one can be called future. So actually, we managed to find an alternative foliation, which shows that we don't have a preferred time in CDT, according to this description. We can define also an alternative parametrization, which measures the distances of these hypersurfaces. Accordingly, how many moves are needed to be done in order to reach from one surface to the other. This is called the beta parametrization. And if this is an analogous parametrization to this alpha, but it does not have to show the same distribution. For example, when the field value is very localized in alpha, then the beta will be elongated. We can see that in the de Sitter phase, we have a quite similar picture. So this alpha and beta parametrization in this phase seems to be equivalent. But for example, if we look at the A phase, we can see a totally different structure. Instead of small condensations, we have some noise-like structure. Also, there are no correlations, except that there are some condensations of this value of beta. I mean, there are some condensations of the field at neighboring beta values. But in phase A, we have also some condensations of simplices and vertices in random places. So this perfectly aligns with our picture that we have about phase A. Interesting that in the bifurcation phase, we have a different picture. I will show you now the distribution of this beta in xt, yt, and zt directions. It seems that in xt and yt directions, we have a correlation, a quite strong correlation with the time. But if you look at the one of the third space-like direction, then we lose every information, as you can see on this pillow structure. Interesting that if you zoom in, you will not see any structure. Doesn't matter how much you zoom in. If you change the beta parametrization into a more finer parametrization, you will also see nothing. It's just noise. It means that we lose one of the directions, actually, one of the spatial directions. We have a spatial dimensional reduction according to this parametrization. This is for the constant equal 2.0. If you look at a value which is even further from the de Sitter phase, then we can see that the xt directions seem to be correlated with time, but we have now two spatial directions which are compactified. So further we are from the de Sitter phase, it seems that more directions are compactified and we have more dimensional reduction. In the B phase, we will have all of these structures as pillows. So just to summarize my talk, we introduced the scalar field in the CDT setup. The field distribution revealed an interesting structure. In every single phase, we had a different structure. We managed to use the redefinition of the field as alpha, with alpha and also with beta. And the corresponding alpha profile and beta profile gave us an alternative volume profile. And also we managed to show that if we consider these hypersurfaces in the time direction, then we can have an alternative foliation, which does not equal with the original slicing, which suggests that there is no preferred foliation in CDT. At last, I will just show once more this beautiful three-dimensional animation, just to show that cosmic fibers are beautiful. Thank you for your attention.
Well, thank you very much. Well, we can thank the speaker. And apparently now we have time to ask questions. So if there are some questions, please do ask them. Well, there is a question by Tomasz.
So could you just repeat what you said at the end about the preferred foliation, because it was quite fast?
Well, I said that with the help of these hypersurfaces, we can, due to the fact that they are fully connected, they divide the configuration into two regions. One is which is behind this, so between 0 and the alpha equal, let's say 0.5. This can be considered as past, and between alpha equals 0.5 and 1, this can be considered as the future of this hypersurface. Because if you transform, I was showing that this transformation of this hypersurface can be shown as elementary moves, elementary three-dimensional moves. And that's why if you go from alpha equals 0 to alpha equal 1, which is the technically equal with alpha equals 0, you continuously, at least discretely, but with discrete steps, but not linear any simplex, continuously shift your hypersurface from this 0 to 1. That's why as it evolves, it will have a past and it will have a future region. So it can be thought of as an alternative time parametrization of the configuration, which does not equal with the original foliation.
Thanks.